Okay. So, I mean, I'm just recalling this. If f is bounded, okay, f is bounded, we proved that we proved that p of x norm square is less than or no, we proved that for any f, we proved that this is less than or equal to integral mod f square d mu xx. Okay. Then we find that using this inequality, we find that the point is tfn minus tf, this norm square, tfn minus tf is actually equal to tfn minus f, okay, norm square. Because, but then for tfn minus f, this is actually tfn minus f. Yeah. And what did we do? Yeah, and this is less than or equal to integral mod fn minus f square d mu xx, right? And this goes to 0. Because of this, tfnx, sorry. There is no tx. I mean, this is not unbounded operator. These are all unbounded operator. You have to act it on something, generally it makes sense. Okay. So tfn minus, so these things imply tfn minus tfnx minus tfx goes to 0. Last time we were struck, but I'm just recalling the same thing, which was sorted out last time itself. So this goes to 0. Okay. Now we know that, but we know that tfnx equal to this. For tfn, if f is bounded, this is equal. If f is bounded. Okay. So tfnx goes to this. So tfn equal to this. Norm of tfnx. So norm of tfnx will go to norm of tfx. But we know that norm of tfx equal to that. This. Okay, with fn there. So it will go to integral fn square. So with all these things, we prove this. Okay, that is how we proved it. Okay. I'm just recalling that. Okay. But the tricky, I mean, the trick is this is equal to this. For that, we have the inequality. From that, it goes. Okay. The reason I'm recalling is we might be using this again. Okay. So first we want to prove TF star equal to TF bar. We have already proved that. I mean, we proved that YTF bar X, X is in domain of, X is in DF. Which is also equal to TF bar, of course. Okay. Then YTFX equal to TF bar equal to TF X and Y. X, TF, Y, X. Huh? TF, Y, X. So this implies that TF bar is contained in TF star. Okay. We have already proved this. We only have to prove that TF star is equal to prove it is equal to that. We have to prove that if something is the domain of TF star, then that is in TF bar. So let Y is in the domain of TF star. So what does it mean by something is in the domain of TF star? If we apply this Y to TFX, this gives a bounded linear functional. Okay. And that is equal to TF star YX, right? This is equal to this. This gives a bounded linear functional. This is well defined. This gives a X going to this is a bounded linear functional. It is bounded linear functional. Okay. And this is equal to this. That is the definition of Y being in the domain of TF star. Okay. And we assume that, and it satisfies this property. Okay. Now we want to prove that Y is actually in the domain of TF or TF bar. Okay, but both have the same domain. That's what we want to prove. Okay. For that, we have to prove the integral equation. That integral is bounded. The domain of TF is DF, which is all those things which satisfies this integral mod f square equal to that it satisfies that. Okay. So we have to prove that inequality. Okay, that boundedness for that. We assume that y is in the domain of TF star. Then we want to prove y is in TF domain of TF bar. Domain of DF bar is that DF bar, the small DF, I mean this DF bar which we define. Okay. So we have to prove that inequality. So for that, let assume I mean we take FB bar. I mean, we want to apply for bounded. So let Fn is equal to 1. So then omega n equal to where f is bounded, where f is mod f is less than or equal to n. It's all those omega for this mod f is less than or equal to n. So 1 omega n f. This is our Fn. Okay. Then this is Fn is bounded. Okay. Now we claim the following. What do we claim? T f bar. So now Fn is bounded function. So bounded function, the domain is everything. It's about, I mean, the operator is also bounded. The domain is everything. Okay. So T Fn bar acting on y, okay, which makes sense. Okay, is equal to E. Now, what is it? PP. P of omega n. Okay, acting on T F star. T F star is an operator. T of 1 by acting on y. Okay. This is my claim. So to prove this claim, I have to prove that this is true for any x. I mean, when you take inner product with any x, I have to prove that both sides are equal. That's what I have to prove. Okay. I take TF bar y. TF bar is a bounded operator. So its star is TF x. Okay. Now this is equal to integral over f mu yx, right? Sorry, fn over omega yx. But fn is 0 outside omega n. So this is just going to be omega n f d mu yx. Okay. I've just written the definitions. Okay. This is my claim. I've just taken the omega n where it is bounded. Okay. So I hope you remember that. Okay. I hope you remember. I have a function. What I have done is the following. I took a y in the domain. Then that y is in the domain of TF star. So it satisfies that. Then I'm taking Fn to be truncated f with this omega n. Okay. So that is, then this is my claim. Let me verify the claim and come back to that. Okay. So this is equal to this. So this is the left hand side. Let us look at the right hand side. Right hand side is P omega n TF star y. Okay, TF star y act with inner product with x is going to be, you can take it, I mean, this is star. I mean, this is well defined for y in omega, y in domain of TF star. So this is equal to, I have to take the P of omega n on to that side first, then I apply TF. This makes sense. Okay. And remember that we have already done this. For any x, if you hit it by P of omega n, where omega n is given by that, which we went through, when we proved that df is dense in whole of h, we used this. P of omega n, when you hit it by P of omega n, when for anything in the, for any x in the range of P of omega n, that is in the domain of df, that is in df. We proved, remember, we proved it when we proved that df is dense. For all these things, this is in the domain. We proved that. Okay. So because of that, that makes sense. TF makes sense on that. Okay. So TF acts on P of omega nx. But anyway, x is in the domain of that. So that's also okay. So this is equal to this. Now this is equal to integral of f over omega. Okay. Mu of y P of omega nx. I'm just writing the definition. Just the definition. This is how TF is defined. Right? TF is defined like that. This is the definition of TF, the very early of proposal. I'm just writing this. Okay. Now notice that what is this mu y p of omega n x acting on a set E, let us say that E is a set in script F. That is equal to inner product of y with P of E, P of omega n x, right? By definition. Instead of x, I have P of omega n x. I have just put that. Now that is equal to y P of E intersection omega n x. Okay. Now this is nothing but mu of yx. Okay. Intersection omega n. Okay. So this is just a intersection measure. You know that if you have a big measure defined on a big set, you have a subset, then you can intersect with that subset, you get a new measure. Okay, that's also a measure. This is a basic exercise in measure theory when you do that. Okay, because of that, this is equal to, because of this verification, this is equal to y. I mean, no, where is this? Sorry, sorry. This integral. So in the integral, we have a measure. Okay, we have a measure. Where is this integral? It is here. This integral. This integral. Okay. In this integral, we have a measure, and that measure is just the mu yx measure intersected with the set omega n. So this is just again going to be omega n f d mu yx. So both sides are equal, right? So hence the claim. Okay. If you want, I will show you the claim. This is the claim, and we want to show both sides are equal. And we show the both sides are equal. If you want to copy, you want to look at something, you can of course look at the video. Just going through definitions, we got that this is satisfied. Okay. T of fn bar y equal to this. Now this implies norm of T fn bar y square. I'm just taking the norm. Okay. P of omega n T f star y norm square. But this is of course less than or equal to T f star y square. Okay. Now we know that this is equal to integral of norm fn square d mu yy, right? Right. So this is less than or equal to norm of T f star y square. MCT by taking limits. MCT, you can take limits. MCT, monotone convergence theorem, is for positive functions. Fn increases to f, then the integral Fn will increases to integral f for that measure. Okay. And if it is infinity, it will be infinity. It's for positive measure. So you can take that for any functions. Okay. Any sequence of functions, increasing function. If one side is infinity, the other side is also infinity. But these things are bounded by this. This is not infinity. So this implies by MCT, we get integral mod f square d mu y is finite. That's what we want. So this implies y is in domain of f, sorry, df, whatever we defined as df, which is equal to df bar, of course. That's what we want to prove. So this implies tf bar equal to tf star. The domain also matches. Okay. We first proved that df bar is contained in tf star. Tf bar is contained in tf star. Then we proved for any y in the domain of tf star, we proved that that is also in the domain of tf, which is equal to tf bar. So this thing proves that tf star equal to this. So in these things in particular proves that, let me write it there, in the proposition itself. This implies tf is closed operator. Because any star operator, t star is closed for any t. So because of the tf is closed. Okay. So we prove that. Okay, I will try to write in small letters because next one is going to be more. I mean, it's the same idea. You can actually, I was planning to leave that as exercise, but it's a bit messy. So I thought better I will do And I mean, I will use something else as assignment. Okay, so this is clear. Okay, if it is not clear, you look at it again. Okay, next we want to prove two functions. So we have two functions. FC measurable. Then we want to talk about the domain of TFTG, the composition. We know the domain of composition, we know. Okay, if we have T an operator, S an operator, then domain of TS is equal to all those X in domain of S such that TSX is in domain of T, right? Okay. This is the domain of ST. That is the domain of ST is defined. Okay. And we want to look at that. Okay. If G is measurable, then we assume that first F is bounded. So bounded. Then what shall we do? F is bounded, so see this implies integral Fg for any measure. Integral Fg is less than or equal to norm F infinity times integral mod G. Fg square is integral mod G square. Okay. For any measure, it will happen. Okay. So because of this, G is contained in DFG. If something is in the domain of TG, I mean something is in DG, then DG is contained in DFG. If is bounded. Okay. From this, what shall I conclude? So these things implies what? Now, first let us look at this implies DG intersection DFG is of course equal to DG itself, right? Because DG is contained in DFG, so DG, and we have to worry about things in DG. Okay. Now let us look at TFTG. So now TF is a bounded operator, so we need not worry about the domain TG. So Y is in. So let Y is in domain of DG. And TFG. So what do we want to prove? We want to prove that with the X. One second, let me just write. We want to write this, right? TFTG X. So now F is a bounded function, so we can take it to the other side as TF bar, okay, Y, okay, which acts on that, acts on TGX. Okay. And that is equal to, so we have TGX, we have that equation. So that is equal to G d mu tf bar y x, right? Is right? Okay. One second. One second. The statement I have thing. I'm sorry. I forgot to. I mean, please change the statement. This is not the statement. Statement is TFTG is contained in. I'm sorry about this. The domain is there. So the statement is this. Sorry. This says something more. The domain is contained and the TFG restricted. See, this is like if you have bounded operator, TFTG equal to TFG. They are equal. Okay. For unbounded operator, TFTG is contained in TFG. That is what I want to say. So the domain is contained and the restriction should be there. Okay. Both will follow if we do the calculation. Okay. So now we have to look at TFG, how TFG acts on that. Okay. So Y TFG FGX. Let me write this. I mean, when we do later all this creation operator, these things will not, we will not have this much complication because we will not work with the domain and all those things. We will assume the exponential domain and work with this. So don't worry that it will not be messy like this. Okay. This is just to prove the spectral theorem, which you are supposed to know when you do all those things. Okay. So that's all. Okay, so don't get discouraged. This is, of course, when you deal with unbounded operators, you can't avoid these things. When you really want to do with unbounded operators. But when we do creation, annihilation operator, they are unbounded operators. We actually don't know what is the domain. Okay, we'll be working on exponential domain and doing that, which is just, I mean, so. But we have to prove that that is something called core or something. For that, we have to consider the domain. TFG X. Okay, now that is equal to integral, by definition, integral of mod FG d mu yx. Okay, so this is by definition, right? Okay. So, I mean, since, see, the point is we have these two equations. Since f is bounded, no, we have to argue again and again. When g is bounded, these two are equal. Okay, and f is bounded, we are assuming. Okay, when g is also bounded, we have proved this. I mean, these two are basically equal. I mean, these two are, we have computed the calculation for general g, but when g is bounded, TFTG is equal to TFG. Okay, they are bounded operators. That is true. Okay, so because of that, when g is bounded, integral mod of g d mu yx is actually equal to integral g d mu, the whatever we have written, TF bar. Whatever I'm just writing it. We have calculated, we have two integrals, no? Those two integrals are equal. I mean, we have calculated the inner product with TFG, inner product with TFTG. TFTG is equal to TFG when T is bound, when G is bounded. When G is bounded, the operator is bounded, so they are equal. So the integral is also equal. Okay. So because of that, T F bar Y X. These two are also equal. So now now you apply the dominated convergence theorem. Okay. Now you apply the, I mean, MCT is enough, I think. Now you're taking the limits. So this will, so by taking limits, you justify that. Okay. This is true for general F, general, any measure of G. Okay. So for bounded, this is true, then you can take limits, and these are just direct limits. You are just multiplying by the bounded function. FGN will converge to FG, and here GN will converge to this. These are all some two different measures, so it will all be equal. So this thing implies the following. So This implies T. Huh? Why is it? Where is norm-FG?
Absolute value of FG.
Oh, there is no absolute value. I'm sorry. It's a mistake by habit. There is no mod. There is no absolute. This is just equal to that. Good. So this implies that TFG. This implies what? We started with something in. We started with the domain of TFTG, right? Well, where did we start with? X is in DG. We started. Okay. So now TFG X is equal to TFTG X for X in DG, and F is bounded. Okay. So yeah, and why is it mod? Okay. So this also does this imply that TFTG? So this is for X in TG. Now we started with X in. This is also, this is certainly, I mean, now F is bounded, TF is bounded. So this is actually equal to domain of TFTG. Right? So domain of TFTG is equal to domain of, domain of G. It is equal to domain, whatever we want to prove. Domain of G, which is also equal to DG intersection DFG, because that is just contained in that. That is what we wanted to prove. Okay. That's what we want to prove. So we have proved it when F is a bounded function. Okay. Now we want to prove when, when G is also, yeah, then we want to again consider G to be bounded function and do that. Now we just take the, when F, this is true for, now we take the norm of this. Okay. Now we take the norm. Okay. Now this implies the norm. Okay. Again, we take the norm. T, no, maybe we have to go through the earlier one. TFG X norm square is equal to norm TFTGX square. Okay. Now this is equal to integral of, sorry. This is equal to integral of G square d mu xx. Okay. That is equal to integral mod G square. This is the technique. D mu, write it properly. This is equal to integral of mod G square d mu. Sorry, mod f square. Mod f square. There we had d square. No? Yeah. Oh, that is because of bar, is it? Oh, yeah. Maybe we should have. Now we want to check for BF. This is okay. Mod f square of y tgx. Okay, right? Now you take G to be bounded. Okay. This is generally true. Okay. TGX. Right. TGX. Correct. Sorry, it's TGX. So there is no Y. I'm sorry. So much. Yeah. TFS TGX TGX. That's right. Okay. Now what do you want to do? We want to prove that we want to prove it in general. Okay. So this is true for bounded F. So this is true. Now by taking limits, this is true for all F. Right? Right? By taking limits, I mean true for bounded F. This is true for bounded F in general for all bounded F and G measurable. Okay. Now Fn converges to F, Fn bounded. I mean, whatever the Fn is a truncated one. Fn converges to F. Then we know that Tfn at X, at any X, I mean, in particular for, in fact, then Fn G will converge to Fg and Tfn X, Tfn X, no? Tfn Tgx, it will converge to Tf Tgx, right? And Fngx will converge to, okay. This is because the earlier trick. Earlier that is why I recalled it again. Fn converges to F, then I mean Fn is bounded, then Tfn will converges to Tfnx. We provided X is in the right domain, okay, which converges to Tfgx. Okay. From those things, so I mean from those things, the integral converges, the operator converges. From all these things, I am just saying this implies that is the domain of TFTG is again equal to that intersection. Wait, no, we have to use the inner product, right? There is the inner product. This implies that y times TFTGX equal to y times TBX implies. Let me just write. This implies y TFTGX. Okay. See, y TFTGX, that's what we calculated. Okay. And that is equal to y times TFGX, right? Holds for all F and G. Okay. I mean, this implies that for all those.
The above thing itself was enough.
Huh?
Like,
which one? This thing?
Yeah, to pretty scroll up. Yeah, so now we can say that TG of X is in the domain of X.
TG of X in the domain of
like
TF.
DF, yeah. TG of X is in DF, right. Implies X is in D of FG.
Right. X is in D of
FG.
FG, correct.
Yeah. So that's what we needed, right? T of FTG, domain of that is contained in domain of TFG.
Yeah, that's what we want. And we also want to prove domain of TFG is exactly equal to DG intersection DFG. Okay. So domain of, so that is what is being proved by this inner product. TFG, right? Okay. I mean, you are right. So this implies TFTG, domain of this is contained in domain of FG, okay, and TFTG X is equal to TFGX for all X in domain. I mean, whenever this makes sense, for all those X such that TGX is in DF, this is equal to that. For all those X in domain of, DF, df such that dg. So dg such that dg acting on x is in df. And the second thing says that domain of df dg is equal to dg intersection domain of fg. No, there is something missing. That is for bounded functions. Sorry, I didn't verify all this.
On like before we showed domain of TFPG is equal to DG by assuming F is bounded.
Yes, right.
Then you assume G is bounded, you get it's also in DF.
We get it?
We get it's also in DF.
Correct.
You assume the other way.
Right. Yeah.
So then it will be there in both DG and DF.
Right.
If you take one at a time. So we just have to show like if X is
now we have to apply it for Gn. I mean G bounded and then take the limits for G.
Yeah.
You all got lost? Eh?
I'm
a bit lost. Okay, I will do this thing again. I will write it clearly and then come with you. I haven't done this. I didn't have time to do that. Looked at it. I'll do it again. Okay. I will not. I'll show that recording. Okay. Okay. Just assume this. Okay. I will prove the spectral theorem. Just assume this. Okay. So this is the theorem we want to do. No, before that, I want to say the following. The final thing about if T is in df equal to h, this is something clear, I think. Df equal to h is equivalent to saying that f is essentially bounded. I mean, f is in, see, what is essentially bounded here? I mean, L infinity kind of thing, but the L infinity is with respect to the spectral measure P. Okay, essentially bounded. Essentially bounded. That is P of there exists AM. There exists AM such that P of mod f greater than m equal to 0. The same definition, but here it's a projection. Okay? I will go through the proof again, more detail. Since we have already gone through and got confused, so it will be clear next time. Okay? Maybe I will simplify it and then come. Okay. Okay. Proof. But if you are interested, you go through the Sundar's book or something where, I mean, it goes through this nice proof with von Neumann algebra, affiliated with von Neumann algebra and other things. It will just take time, and that's very clear. I mean, you don't go through all these things. It's very clear. First, you work with, see, the thing is, what is the example of the spectral measure? I haven't given that, right? You take your H to be L2 of R, for example. Okay? L2 of R. Now on this L2 of R, any function, if you take any function f, okay, any function f, will act on this. I mean, will act on this with the domain. I mean, you take the df is equal to all g in L2 of R, such that fg is also in L2 of R. That's all. which will be precisely those functions for which so now this you can define the multiplication operator from L2 of R to L2 of R with domain df. Okay, domain of mf equal to df. Okay. So you get operators. This will be bounded operators. Of course, f is bounded, then f is L infinity essentially bounded, then you get a bounded operator as usual. So if you take indicator functions, 1e, okay, the multiplication by 1e is a projection. You can call that as P of E. This gives a spectral measure. You just take the indicator function, P of E equal to multiplication by the indicator function. P of any set is multiplication by 1e, which is a bounded operator, which will be a projection because 1e square satisfies that condition. Because we are in, 1e takes the real value, so it is self-adjoint. And you can prove that it's a projection. P square equal to P because 1e square equal to 1e again. Okay. So because of that, this is a projection. And this will give a spectral measure. This is an example of a spectral measure. In fact, our example is also, if you look at it, you are actually considering your H as a sum L2. Okay. And then for any function, you are having the F square. You are just dealing with actually multiplicative operators, basically. So if you go through that proof, which is same as this proof anyway, so it will all be clear. It will be more nice. So I want to prove this. If f is essentially bounded, so it is. We have already proved that if f is essentially bounded, the domain is everything. We know that. Okay, this way is clear. Okay. F is in L infinity of P, then df equal to h. On the other hand, if df equal to h, we know that tf is closed. We have already proved that tf equal to tf bar is equal to tf star. So tf is closed. Okay. Tf is equal to tf bar star. So tf is closed. Okay. So this implies tf is bounded. Closed graph theorem. And we are applying closed graph theorem. Theorem, TF is bounded. Okay. Okay. Now, why is it true? Now let X is in P of this set as usual, mod of greater than or equal to n. Okay. Some X is there. Then TFX square equal to integral f u mu xx mod of square. But then X is in mod of greater than or equal to n, right? X is in that. We have already gone through this proof. This is equal to, this is over omega, mod of greater than, it is over this set. The integral is just over this set, okay, of mod of square. On this is greater than or equal to this. So n times, the total measure of mu xx is norm x square. That also we have seen, right? Mu xx is a positive measure. The measure of the total set is norm x square. So on this set, this is greater than n square. And the total measure of the set is norm x square. No, there is a problem, no? I'm taking greater than or equal to, right?
So it's bounded. So
no, wait a minute. No. This is greater than d mu xx, I cannot say, no? This is equal to, See, this is equal to, this is greater than or equal to mu xx of mod of greater than or equal to n. That's what I can say. Why is it greater than norm x square? That is not greater than norm x square. Tfx square equal to norm mod of square. Inequality is, you understand the point? I mean, I said norm x square. I want to prove that x is 0. That's what I want to prove. That's what I want to prove, right? I want to prove it is essentially bounded so that the P of that set should be 0. So x is in that set, then I have this inequality. So Tfx square is greater than or equal to n square times mu xx. This is not true. I don't know.
So I don't think you can do that.
Do what?
I mean, the middle equality you don't need. You just
No, that equality is okay, no? Because x is in that project, that domain. Okay.
Yeah.
Then
that doesn't
the,
mean your own integral.
no, then mu xx, mu xx of the complement is 0. So this is equal to norm x square only.
Yeah.
Mu xx is just the,
You can directly go from that one to the last.
yeah,
norm x.
yeah.
You don't need
So. Oh yeah. Okay. This is okay. This is equal to norm x square. Okay.
Yeah.
Yeah. I mean, mu xx is concentrated on that set. Okay. And it does measure norm x square. So that is equal to this. Okay. So this is okay. And the function is summing. Yeah. This is okay. Okay. Now let us write the spectral theorem. I mean, I will prove that multiplicativity of that domain property. You do the following proof, which is very easy. Now we are almost set with everything, every tool for spectral theorem, except that we are going to use it the bounded case. Now T be an unbounded operator. Then there exists, actually it's unique. Uniqueness we will discuss later. Okay. Unique spectral measure P from Borel sigma algebra or to unbounded operator on H, okay, to P of H, such that T is equal to integral over X d dp. Okay. So that is, I mean, T is just the Tx. That is this function. I mean, this function f from R to R is just T going to T. Okay. Then T is equal to TF. That's what I'm saying. And this is just a symbol. Okay. X dpx is just a symbol. T is equal to that TF. So I want you to write the proof, sum of the proof. Okay. I will give you the proof. I'll sketch the proof, fill up the details, and write it as an assignment. Okay. So let R is equal to T minus I inverse, which we can define. We have proved a theorem that T minus I, the kernel of T minus I is 0, singleton 0, and the range is everything. So it's invertible and it's also bounded. So this is a bounded function, bounded in B of H. So there exists a spectral measure, unique spectral measure on sigma of R, which is a compact subset of C. Okay, sigma of R, such that R is equal to integral over Z D spectral measure. You call the spectral measure as, so I want to use some other notation because I want to use P for this. So there exists a P prime. P prime. Okay. D P prime Z. Okay. I mean, this is just a notation. This is just a spectral measure, but the set is contained in the omega is contained in C. Okay. It is just this. Okay. Now define phi from R to C by T going to 1 minus T minus I. Maybe I remove I. I mean, it doesn't matter. You can use I also. Okay, let me take this I also. Almost surely for T not equal to I. Okay, for T not equal to I. But we only need, I mean, measurable function, which is defined almost everywhere is what we need. Okay. So on measure zeros, we can remove your measure zero set and you don't care what happens there. Okay.
Just from R to C.
Huh?
From R to C.
R to C, correct.
So how will it be?
Oh, sorry. But the other way only we have to worry. No, this is okay. This is okay. When we integrate it, when we integrate it, we have to. Sorry. Yeah, you are right. This is okay. So this is from R to C. There is no problem. When I write the integral, I have to worry about it. Okay. So, this is okay. Now, from when I write the integral makes sense because where the I is, there is an open set around I where the measure is 0. Okay. Now, sigma of R is contained in C. Okay. And I is not in sigma of R. Okay. This is a compact set. Is compact. Okay. Now, I is not contained in sigma of R. This implies there exists a open set U which contains I such that U intersection sigma of R is empty. Okay. So the inverse is bounded. What am I trying to do? I want to say that integral over Z. Let me write it clearly and then I will get it. Okay. Integral over Z d P prime Z is what we are having. Okay. That I want to say that is equal to 1 by P minus I dpz. Okay. Where P of any set E is contained in R equal to P prime of phi of E. I mean, notice that phi is a one function between the range and domain, between the range and domain. I mean, it's a invertible function between the domain and range. Okay, so P is equal to P prime is equal to P phi inverse. Okay. Okay. So integral Z d P prime Z is equal to integral over P 1 by, which is same as integral Z d P phi inverse T, phi inverse, sorry, phi inverse Z, which is equal to integral by the function phi of T dpt. Is that okay? Just integral of 1 by T minus I dpt. 1 by T minus I dpt. See, you had a measure, spectral measure P prime on the complex plane. Okay, now you have a function phi which is defined from R to complex plane. Okay, now you define a new spectral measure on the real line such that P of any E is equal to P prime of phi of E. That is, P prime is P phi inverse of E. I am writing it this way because our operator is 1 by T minus I. So that is why I am writing. This is the better way of writing it. Okay. Otherwise, you have to consider the inverse and the function is defined on R. Okay. Now we got a news, and when you can verify that P is also a spectral measure. Okay, because it is just written as inverse of something. I mean, it is indeed inverse of something. Because it is a 1-1 map from domain to range, it's actually, so P is a spectral measure. I want you to write the whole proof. Okay, I'm just sketching the proof. Even if there is a mistake, you do that. Okay, that is assignment. Okay, P is the spectral measure. You already have to do something on annihilation creation operators, no? So hope you have done that. I mean, when do you plan to submit assignment? You can take your time, but I have to submit marks by December 15. So it's better you give it by the end of this month or first week of December. Okay. I mean, after midterm. Okay. Sorry, after end term. I'm confusing with everything today. Sorry. So, P is spectral measure. Okay. And we got this. But you can easily see from this, I want to conclude the following. Then the assignment is to prove. I mean, these are all till now just definition. Okay. You can easily verify that P is a spectral measure. P prime is a spectral measure. P is also a spectral measure because it is just you have taken it inverse basically. So I mean, you can inverse means not inverse measure. Okay, so that will give you a measure. Okay, that from the measure theory course you will know that. But the point is you want to prove this. Now prove that T is actually equal to integral over T dpt over R. So to prove this, I mean, it will be more or less clear. You can prove that T minus I is equal to integral T minus I dpt. You can just prove it because you already know that, I mean, 1 minus T minus, you have this equation, right? 1 minus T minus I, that is equal to this. So here it is T. Pardon. This is T. There it is 1 by T minus I dpt equal to that is an operator, right? That is your R. Okay. That is your R. Now that R is 1 by T minus I inverse. Now you can assume that T minus I, you can write it as T minus I like this. The point is, it's not simple. You have to worry about, in bounded case, it's simple, but here you have to worry about the domain. So what we have to do is the following. Define, this is how the proof should go. Define some S is equal to T dpt. Okay. You have already P prime, you got a P. Okay. Now you define S is equal to T dpt. Then first claim is domain of S contains domain of T. Okay. And S is yes. We want to prove S is T is contained in S. That means both the things. First claim is T is contained in S. So how do you prove that? You have to prove basically T minus I is contained in S minus I. Okay. It's a you have to prove T minus I is contained in S minus I. So how will you prove that? If something is in the domain of T minus I, where T minus I means the domain means mod T square dpt, that is less than infinity. That's what it means by something is in the domain of T. Okay. Then you have to prove that is in the domain of this S. Sorry. S is defined like that. Sorry. S is defined like this. T is just T. Sorry. We have a original T. I'm sorry. We have originally some T. Okay. From that, we have T minus I inverse, which is actually given by some Z, dp prime. Okay. Now you know that, see that T minus I inverse is an operator from H, which maps onto whose range is domain of T. That's very important. Whose range is domain of T. Okay. Okay. Now you have to prove that something is in the domain of T will look like this. So you called it R. It will look like R of some Y. Some X is in domain of T means X looks like R of, there exists a Y such that there exists a Y such that R of Y equal to X. Okay. Now in R of Y, if you apply T minus I and also S minus I, they will be same. You can verify that. By that, you should prove that actually X is in, if you work with this condition, if you remember this fact, then you can prove that T is contained in S. But now we know S is defined as a operator, multiplication operator like that. Spectral operator, integral T. So that implies T is contained in S. Now oh my God. The most important thing I forgot, T be a self-adjoint or bounded operator. Okay. That is why all these things works. I'm sorry. Self-adjoint, that is why we proved all these things, no? The kernel of T is 0. That's all for self-adjoint operator. I'm sorry. The T is self-adjoint operator. Completely forgot to mention that. So T is a self-adjoint operator. Okay. So this implies T is contained in S will imply T contained in S will imply S star is contained in T star, which is equal to T, which is contained in S. Okay. Now we know that S is a closed operator. So this implies S star is nothing but integral over T bar dpt. But T is over R. So this is equal to T dpt. So S is equal to S star. This implies T is equal to T. This implies S is equal to T. What I am saying is, first you have to prove T is contained in S. Domain of T is contained in domain of S. You remember this fact. Anything in domain of T is actually Ry. Okay. Then you apply it, then you can prove that domain of T is contained in domain of S. And it is the case that S of Ry is equal to T of Ry. That is clear. S of Ry equal to T of Ry because S is defined like that. First you prove that. That implies T is contained in S. Now, by taking star, S star, we proved that T is contained in S, then S star is contained in T star. It will go through the definition, it will just follow immediately. There is nothing to prove. So because of that, this is true.
Sir, on the beginning, when you said that there's a spectral measure for R, right?
Hmm.
Did you use like spectral theorem for
Of course,
normal operators?
of course, normal operator.
Um,
Yeah. That is where I misjudged the whole thing. I mean, that I thought, I mean, actually, you can get a unitary. It's enough for unitaries. Actually, this is not unitary. This is just a normal operator.
Mhm.
But you can take t plus I by t plus I, that function. That will give you a unitary, which is what is called Cayley transform. I avoided all that. Okay. I mean, that's you have to use this function, t plus I by t minus I. This function, that will give you a unitary. Okay. So I thought that its unitary is enough, but that for then I had to prove that unitary actually comes from a self-adjoint. That I don't know how to prove without self-adjoint. I mean, spectral theorem again. I mean, so the whole thing I couldn't avoid. I need general normal operator. So then I thought I can general normal itself. I can use it here. Okay. So assignment is clear. You have to prove the spectral theorem. That's all. For that, you have to just do this. Okay. Okay. I will recall all these things in the next class. I mean, wherever I have got confused, wherever confused, I will recall that. Then we will go to Fox space again. Okay. So if we need anything else in the next course or something, then we will prove it. I mean, whoever is attending, we will prove that again. Okay. I hopefully that will be better course.